Hello and welcome to Bengal Banter. I'm Alex Sanchez. Bengal Banter is filmed and produced right here on the campus of Idaho State University. Today on Chemistry Corner, we have Todd Morris, who teaches chemistry here at Idaho State University. Hello, Todd.
Hello, Alex.
So what do we have here with us on the table?
Well, today here on Chemistry Corner, just like all times in Chemistry Corner, we're going to demonstrate and, more importantly, learn some chemistry with household materials. So specifically today, we're going to learn about the kinetics of a chemical reaction. The kinetics of a chemical reaction is just how we say how fast a reaction goes. Okay. So some chemical reactions happen very quickly. We'd say that has very fast kinetics. Some chemical reactions happen more slowly over days or years. We say that has very slow kinetics. Okay. And so specifically, we're going to look at how we can measure the kinetics of a reaction and also how we can change the kinetics of a reaction, either speed it up or slow it down. Okay, so first things first, safety. Yes. What do we need? Safety. So we are dealing, even though we're dealing with just simply household chemicals, we do want to take into account safety. So we're wearing our lab coats in case we get any chemicals on us that won't stay in our clothing. We have goggles to protect our eyes. Our eyes are most exposed to any sort of chemical. So we'll go ahead and put those on. All right. And then we also have our gloves just to keep the chemicals off our hands if we need to. And you said we have Clorox and food coloring? Yes, we have Clorox and food coloring. So the chemical reaction we're going to be looking at is just simply the reaction of bleach with these different types of food coloring. Bleach is has lots of different applications. One of those applications we know of is that you can add it to your laundry to get rid of those stubborn stains that you might get on your white shirt. Right. And in those cases, the bleach is reacting with those colored stains and making them invisible, making them colorless. Okay. So the first thing we're going to do is just get an idea of some of the factors that affect how fast a reaction goes. And so we have a couple drops of yellow food dye in water in this plastic bottle. We have a drop or so of blue food dye in this plastic bottle. And so what we're going to do is we're going to add the same amount of bleach to both, and we want to get a feel for how fast does the bleach react with this substance versus how fast the bleach reacts with this substance. Okay. So when I add bleach to these substances, how would I know that the reaction is over? What am I looking for in the substances? Depending on how fast or slow they are, I'm not sure. I would assume that the blue is going to be the reaction to the blue is going to be a lot slower than the yellow. But that's my assumption. Okay, so that's your prediction. What are we looking for to let us know that the reaction is over, though? So when I add the bleach, how would I know the reaction's done? In other words, would they go colorless? Yeah, they go colorless, exactly. So we know the bleach is going to react with the food dye and render it colorless. Okay. So that's what we're essentially looking for, is to either time it specifically, like watch the clock, or just kind of get a feel for, this took about 10 seconds and this took maybe 2 minutes or 10 minutes. Okay. So we have our yellow food dye and our blue food dye to begin with. And so go ahead and take the cap off each one. And we're going to add approximately the same amount of just household bleach to each one. And I'm adding about 20 drops of bleach to the yellow. And then I'm going to add 20 drops to the blue. So in science, we like to do an experiment where we don't keep everything the same, except we're just changing one thing. Here we're just changing the color of the food dye. And then go ahead and put the cap back on. All right. So same amount of bleach, different food dyes, kind of give it a shake to mix it up. Wow, that one's already colorless. Yeah, the yellow one's already colorless, just within a second or two. Even if you notice very carefully, even before I had a chance to even shake it up, half of the solution was already turning colorless. Yes. So even that shake of 2 seconds was enough to render it completely colorless. So we can say then that for this particular reaction, bleach is able to react very quickly with the yellow food dye. I was right. You're exactly right. As opposed to the blue food dye, we add the same amount of bleach, and it's been about 20 or 30 seconds at this point. Right. And what can we say about the color in the blue bottle? It's beginning to be a little bit less bluish at the bottom, but not much. Yeah, I agree with that. That it's starting. It's still definitely blue. Yeah. But it's starting to fade a little bit. And if we give this maybe, rather than just 1 minute, if we give it 5 minutes or 10 minutes, eventually this solution will look exactly the same as this solution. So in this example, we have the bleach react with the yellow food dye very, very quickly. Just a few seconds is all it takes to fully react. With the blue food dye, it may take several minutes. So we'd say that it reacts very quickly with the yellow food dye, very fast kinetics with the yellow food dye, and very slow, relatively slow kinetics with the blue food dye. So those are our results that we got with yellow food dye and blue food dye.
Okay.
We have a third experiment set up here. This is a green colored solution. And what do we know about green colored solutions?
It is
what makes it green?
A mixture of yellow and blue.
Exactly. So yellow and blue makes green. So this is a green food dye that we've added. It's essentially a mixture of the yellow food dye we use in this experiment and the blue food dye we use in this experiment. So based upon these results, what we like to do in science is to make predictions as to what's going to happen in a third experiment. So if I add the same amount of bleach to the green solution, what kind of observations do I expect to happen? What do I expect to happen in this reaction?
I would assume that it would take longer for it to become colorless. Would it not? Or
okay, so you expect to take longer to go colorless because you have maybe two colors in there.
Right.
Do you expect it to go from the green to the colorless, or do you expect something else to happen in between those?
For example, go from green to yellow or green to blue and then colorless?
Right, for example, yes.
That could happen. I'm not exactly sure. That's very interesting.
Okay, so let's see. So we kind of have maybe some educated guesses what may happen when we add the bleach to the green food dye colored solution. So we have already added the green food dye. So I'm going to have you then add, just like I said, a dropper full of the
Oh, you want
the
me
bleach.
to do it? Okay.
Yeah, go ahead and do it.
All right, cool.
I think you've mastered it from watching me earlier.
All right.
So add add that, and then add another one full.
All right.
Okay, and then go ahead and cap it, give it a shake, and then we'll see if our predictions were right.
Oh, we went straight to blue.
It went straight to blue. So initially it was green, and then within just a few seconds it went from green to blue, and then after it goes from blue, it eventually go to colorless. So in this example, we can explain that because this is, as it says, a mixture of the yellow and the blue food colorings. We saw earlier that the bleach reacted very quickly with the yellow that's present, and so you take a green solution and you remove the yellow, then you're left with the blue solution.
Okay.
So we get the blue solution that will eventually go to colorless the same way that the middle blue solution is also eventually going to colorless as well. Make sense?
Yes, it does.
Okay, good. So when we're measuring, so you get an idea of how fast the reaction goes by measuring how long it takes, whether it takes 10 seconds or 10 minutes for the reaction to take place. But we also can change how fast the reaction actually goes.
How so?
Well, there are several different things we can change. Probably the easiest one, and probably the most relevant one to our common daily lives, is we can change the temperature of a reaction. So here I have the same amount of red food dye added to a bottle of room temperature water, and we have also relatively warm water that I got from just simply hot tap water. And so we're going to once again repeat the same experiment by adding a little bit of bleach to both of them, shake it up, and then watch what happens to get a feel for in which case do we have faster kinetics, which case do we have a faster reaction.
I would say the warmer
Okay,
water.
so you predict that the warmer one will be faster, so this one should take less time to get colorless as opposed to this one.
Yes.
Right? Okay,
That's
good.
what I'm predicting.
So that's our prediction. So we have a hot on my right-hand side, and the warm room temperature on the left-hand side. So we'll go ahead and I'll add, let's say, 2 dropperfuls to the room temperature solution. And if you want to add 2 dropperfuls to the hot solution. Okay, one more. Okay, perfect. All right.
Right there.
So let's cap yours. Give it a shake. Count of 3. 1, 2, 3. And then set it back down. And then make some sort of observations as to what happens between the room temperature solution, room temperature reaction, and the much warmer reaction. So you predicted that the much warmer reaction you thought would happen a lot faster, react much faster.
So
it should take less time to go colorless as opposed to the room temperature one.
Looks like the room temperature is going, the reaction is happening faster. That's my observation, but I could be wrong.
Let's give it a few minutes, a few moments. I'll give them both
another shake.
So I think what you have, so it looks like the room temperature one is actually going faster than, they're about tied almost.
Yeah, right, they're about the same.
And I think what happened is that one of the other factors that we won't talk about that affects how fast the reaction goes is how much of the substance is reacting with how much of the substance. So if when I added my bleach, if I added more bleach than when you added your bleach, then I would make my reaction go faster even though it's a cooler solution.
Right, I could have
lower temperature.
Less. But originally, what should have happened?
So what should have happened is that, assuming everything else is the same, we'd expect that, as you predicted, that the hot temperature solution will react much faster than the room temperature solution.
Okay.
And we take advantage of the fact that that chemical reactions generally take place a lot faster at higher temperatures, because when we're cooking foods, generally when we want to cook foods, we want to cause physical changes, especially chemical changes, to occur in our foods. We want to make the vegetables taste good. We want to make the meat palatable, otherwise it'd be very chewy if it's undercooked. And that's going to take place a lot faster at higher and higher temperatures.
Of course. Yes.
The converse is also true, that if we want a chemical reaction to be very, very slow, such as the spoilage of food that naturally happens, we keep those foods in the refrigerator, because in the refrigerator temperatures, those natural processes will still happen, but they may take days or weeks to happen rather than maybe a few hours if they were left out on the table.
Interesting.
So it's been a few minutes, and so I think actually our initial observations were wrong, that definitely the hot temperature is definitively colorless at this point, whereas there's still at least a little bit of color left in the room temperature water. So your prediction was true. The reaction experiment worked exactly as it hoped we would.
Yes.
And we saw that at higher temperatures, the reaction is much faster than it would be at lower temperatures. Any questions?
So what does it take to, like, if you're interested in chemistry, what classes do you need to take to learn this sort of? Is this advanced? Is this low level?
Well, this is actually something I would normally teach in my freshman level general chemistry course. Okay. Generally in chemistry, there's a lot of math involved, so a lot of times you might have to take some earlier maths in order to have enough just skills in the math to do the chemistry that's necessary. But this is something we talk about just even the second semester chemistry, to talk about kinetics. Of course, in the actual class itself, we go into the whys of why it's faster at higher temperatures and slower at lower temperatures.
Okay.
But so kinetics is relevant to what we do. We have some chemical reactions we want to take place very, very quickly, such as the medicines you may take for your headache or your stomach ache. You want those to work within minutes rather than with hours. Whereas other reactions, we want to have very slow kinetics, such as the rusting of your car outside. You want that to be as slow as possible. Right. And so there are things we can do to either speed those reactions up or slow them down. And one of those factors we can change is the temperature of the reaction.
All right, well, thank you, Todd, for giving us this amazing lesson. Thank you for joining us today on Bengal Banter, and have a nice day.